Thank you.
Yeah.
Okay, good. Yeah, so this is about the matching problem using Quasi-NC. So it's joint work with Jakob, my student at TPFL. So let's see. So I guess most of us know the matching problem. So given a graph, can you pair up the verses using the edges? So can anyone see a matching here? We'll ask a lot of questions. This is probably the easiest one. So you see here. All right. So jokes aside, so this turns out to be a pretty tough instance. So this is a good counterexample why the non-bipartite graphs is harder to deal with than the bipartite graphs. Okay, so we will see later on in the talk why this is an obstacle. So the matching is there. Okay, so of course this has a long history. So it's Jacobi and Edmonds. So Jacobi is attributed to giving an algorithm for the bipartite case that is efficient. And
I mean, you can read the paper actually.
Okay.
It's yeah, it has
nice.
It's 1890.
1890. Yes, so impressive person, of course. So for general graph, it took them 75 years to get down to general graphs, like polynomial time. That was Jack Edmonds. And then, it's a benchmark problem in many models of computation. Here we will focus on parallel. Okay. So what do we mean by parallel? So we will be interested in problems that basically parallelize completely. So I allow you to use many processors, unreasonably many. So polynomially many processors, and but using that many processors, you want to run extremely fast, like polylogarithmic time. And the question, one of the main questions here, I think, is whether matching is in NC. Okay, so that this remains open. And this is intriguing because we have known for quite some while that if I allow the processors to use randomness, then it is in NC. Okay. Yeah. So for the decision version, this was proved by Loas in '79 that we can do it in randomized parallel time. The decision, but here actually the search version turns out to be much more complicated. This was first solved by Avi, Kapp and Uffol in '86, and there was another algorithm the year later by Mummi, Vatsani. Okay. So today we know both the search and decision versions are in randomized NC, but we don't even know if the decision version is in NC without the randomization. So this fits into the general paradigm if we can de-randomize all efficient computation, which seems believable but hard to prove. So a more modest goal is could we at least de-randomize one of these algorithms. Okay. So what is known? Even if we don't think about de-randomizing one of these algorithms, let's say what kind of graph classes can we have a faster parallel algorithm for matchings? So a lot is known, okay? So if you get special don't read all this, but a lot of special graph classes have been solved. Maybe for planar graphs, for example, you can count, surprisingly. So the decision version for planar graphs have been solved for quite a while, and this year, or last year, it was solved by Anna and Vatsani for the search version. But in spite of all these graph classes, one very natural graph class remains open, and that what Jacobi solved then 150 years ago. So we thought we understood matchings for bipartite graphs. And a major progress for that graph class was achieved 2 years ago by Fenner, Goya, and Tirov. Okay, so they proved that bipartite matching is in Quasi-NC. So Quasi-NC is the same as NC with the difference that here I allow you to use even more processors, so quasi-polynomially many processors. Okay. So it's a theoretical result. So and polylog and time, and it's deterministic. So these are the gentlemen. So yes, we will see. I will talk a lot about their paper. That was the main influence. So very nice paper. But and here it turns out that the graph I showed you in the beginning is a good obstacle how that method generalizes. So we will see how their method fails on that graph and then how to tackle it. Yeah, and as the title was pretty clearly saying, we prove it. We remove the restriction for bipartite graphs. That's our result. Okay. With quasi-polynomial processors. So actually, you will see. I hope during the talk it will be clear that this is not, a technicality. That is kind of a limit with the approach. So it seems like to remove this quasi-polynomial to make it polynomial seems like it requires fundamentally new ideas. Okay. Any questions? Okay, so let's see. So what I want to say is what's the basic approach we use? And then I will explain, basically the whole proof of the bipartite case. And then we'll see what are the obstacles for the general case and how to overcome them. So Rohit gave a very nice talk at Stock. So I think it's almost the only result I managed to understand the proof during the talk. So that's why I thought maybe I can work on this problem. Because it felt like I could work on the general case. So hopefully I have more time than him. So hopefully I will be able to explain their proof as well. Okay, so basic approach for de-randomization. So we want to get a deterministic algorithm. You could think of cooking up a completely new algorithm, right, that runs in parallel time. That's what they do for planar graphs. But here, we would like to select one of the randomized algorithms to de-randomize. And here, we select the one by Mulmey-Vatsirani. And the reason being that you can separate out the randomness quite easily in that algorithm. So it's the way you use the randomness is very easy in some sense. So in the first step here, it's the only place where you use the random, is that you select the random edge weight for each weight from 1 to n squared, let's say. Okay, and then you calculate some. Then the second step, you have a deterministic calculation. You calculate some determinant of something called a Tat matrix, and that's the whole algorithm, basically. Okay, so one thing we should note here is that when we calculate the determinant, we insert some values that are exponential in the edge weights. This is important because this means that the weights we select in the first step needs to be polynomially bounded. This is important because otherwise the problem becomes, that I will talk about, becomes trivial. So this restriction really is important for the core of the problem. So they have these two steps. They also give a very nice criteria when the second step is guaranteed to work. Okay, so it's guaranteed to work when the weight function is isolating, meaning that if I manage to select the weight function.
Hold on, just before, maybe it's good to say that the second step has a fast parallel algorithm.
Yes, good point. So this step here is the way to calculate the determinant. It has a fast parallel algorithm, and that's also what Lovas used in his paper. So I think maybe Avi can correct me, but I think all these algorithms use that determinant can be calculated. Yeah, very good. So step 2 is guaranteed to work if the weight function is isolating. And they combine this with what is now called isolation lemma. I don't know if maybe they call it isolation lemma. So they show that, if I select the weight from 1 to n squared, let's say, with high probability I will have an isolating weight function. Which at first sight looks surprising, right? Because there's only polynomially different weights we assign to matchings, but might be exponentially many matchings in the graph. So most matchings have roughly the same weight, but the minimum is unique with good probability. So the minimum is very special. So now to de-randomize, we can ask ourselves, can we replace the first step? On input the graph G, can we construct a weight function that is isolating in NC? Okay. Of course, we could do it in polynomial time, just solve the perfect matching problem, output, weights that makes that the minimum weight. But here we have to do it in a more restricted manner. So that's our challenge. Can on input G construct an isolating weight function in NC? So we don't want to get bordered in what we can do in parallel time. So let me give you a cleaner challenge that is oblivious in the following sense. I don't give you the graph as input. I only tell you the size of the graph. Now you don't want to construct one weight function, but you want to construct a family W of weight functions. Well, they have to be of simple structure, but they will be on a simple structure. And this family should satisfy that any graph on n vertices, there should be an isolating weight function in this family. Okay. So instead of saying on input G, construct me a weight function, you just tell me the size of the graph, and now I want to construct a family of weight functions. So that when you give me a graph, one of them is in particular isolated. Now I need to have two constraints on the weight function I construct. So because I want the algorithm to run fast, I want them to be polynomially bounded. Remember, in the second step, we replaced by 2 to the power of WE. And then when we run this in parallel, we will just try all the weight functions in parallel. We are guaranteed that one of them will work if the first condition holds. So we want that the total size of the set is bounded. So this would give like an oblivious de-randomization. Okay, so the oblivious parallel algorithm just runs all the weight functions in parallel. Because of the first condition, one of them is guaranteed to work. So let's get a feeling for this by removing. So I said that the second condition is important, otherwise the problem becomes pretty easy. So can anyone construct such a family W star if I don't have polynomial edge weights? Yes. Okay. So one way would be, maybe it's okay. It seems like you think this is easier than the initial question, which I find surprising. One way would be, to just say, set this to be 2 to the power of I. Now the weight of the perfect matching is dominated by the heaviest weight. Okay, so that would be isolating. So now actually we could have a family of a single weight function that would be isolating for all the for all the vertices, all the graphs of n vertices. What if I restrict the third guy? Well, then it's clear, right? I can select the whole family of all the weight functions. The isolation lemma tells me most of them will work. But what is interesting here is that, to my knowledge, the best thing we know, if I have the conditions 1 and 2, the best bound we have on the cardinality is exponential. Okay. So we don't know anything more than the trivial thing here. So now to get quasi instead of NC, what we do is to replace poly here by quasi-polynomial. Okay. Both in terms of the ranges and the size of the family. And that's what they prove. Okay, so this family exists for bipartite graphs, and we prove that such a family exists for general graphs.
This means easily constructed.
Yes. So this, we will see. Yeah, exists. Oh, okay, good. I think it's not hard to prove that this exists by just randomly sample, and then you have by isolation. Yeah. All right. So that's what we're gonna address. Okay. So bipartite case. So what's the main idea? No, well, not maybe main idea, but one of the main insights. So maybe you've seen this movie, the Wall Street, about greed. so what do you think is the main insight? Okay, I gave this talk, but then Lucas said they saw the end of the movie, so they realized they should not be greedy. So let me explain. Let me explain.
You're already thinking about the non-bipartite case.
No, maybe. Yes. Right. Okay, they're greedy in the selection of problem, but non-greedy in the approach. So let me explain. All right. So we wanted to have a family that was isolating. Okay, here's a nice family of weight functions. You start with this trivial weight function. Now you take mod k. For each k, you get a new weight function. Okay, and you take mod a polynomially many primes. So this will have nice properties. We will see later on. Okay, so this is a nice weight function that we can easily construct. Now we would like to prove that for every graph now of n vertices, one of these weight functions would be isolating. That's greedy. So let's be a little bit less greedy. So they select some weight function W1 from this family. Then we look at the set M1 of matchings that minimize this weight function. If M1 would be a single matching, you're done. But it might be bigger. So if it's bigger than one matching, what they do is to select a second weight function from the same family. And now they let M2 be all the matchings out of M1 that minimizes weight 2. So basically, you first minimize W1. Subject to the matchings that minimize W1, you now minimize W2. So it's lexicographic minimization. And now you select W3, and you let M3 be the matchings of M2 that minimizes W3. And you continue. The question is, how many weight functions do we need to select from this family in order to find an isolating, that there is only one remaining matching? You see, if we could prove a bound on L, this would give us a oblivious de-randomization, because that would mean that we could try all possibilities of selecting W1 and WL in parallel. There is polynomially many choices of each one of them, so the total number of choices would be n to the power of L. Okay. And what they prove is that there is always log base 2n such functions to choose. And this this is now lexicographic minimization in the sense that you minimize W1 subject to the guide that minimizes W1, you minimize W2 and so on. You turn this into normal minimization by just putting a much heavier weight on the first weight function and so on. So this is the family of weight functions that they consider. That's also why they have quasi-polynomial range.
So the quantitative for any g, so the
yeah. But now our problem is the following. You give me G, and now I can spend as much time or, as much as I want to just show the existence of W1, existence of W2, and so on. I think most of us will be able to prove this easily if you were allowed to choose n weight functions or something like that, right? You just remove some matchings each time. But here we want to be much better. We only want to select log base 2n weight functions. So somehow we would need a good progress measure, right? Because somehow there's exponentially many weight matching. So even if you halve the number of matchings you get each step, that's not good enough. So this is our goal. So to understand the progress measure, let's look at when a weight function is not isolating. So we have a weight function W that is not isolating, meaning that there exist at least two perfect matchings of the same weight, of same minimum weight. So we have the green matching and the red matching. What do we, I think I only know one thing to do when you have two matchings. So you take the symmetric difference, okay? And you get alternating cycles. What can we say about the weight on an alternating cycle here? The weight of the green edges compared to the weight of the red edges. Notice that I can always form a new perfect matching by taking these red edges, this red edge, but then flip this cycle to take these green edges. This should lead to a matching of, not bigger weight, actually of not less weight, but this means that, they have to have the weight of the green edges here have to be the same as the weight of the red edges, because otherwise you could always combine it to an even smaller weight matching. So what I'm saying, sorry. So let me say that so if the weight of the red edges were less than the weight of the green edges, I could always take the green matching everywhere else. So I take this green matching, but then I could take a better choice here, leading to a smaller weight than the green matching. This is a contradiction, right? Because I started off with two matchings of minimum weight. Okay? So this means that for a weight function to not be isolating, the discrepancy, they call it the discrepancy, so the weight of the red edges minus the weight of the green edges, the discrepancy needs to be 0 along these cycles. So this gives us a goal. In order to find an isolating weight function, a sufficient criteria would just be assigned non-negative weight discrepancy. Find a weight function W so that all the cycles have non-negative discrepancy. Because, this shows that if I have two matchings of minimum weight, there must be a cycle with 0 discrepancies. If no such cycle exists, I will be fine. Okay, so progress. We will see that, so, there are many cycles, so this seems like a tough goal, but maybe we should be less greedy, so we can assign non-zero to some of the cycles. Okay? Yeah, so a graph may have exponentially many cycles, so it seems hard to find a weight function that assigns non-zero discrepancy to all of them. But, because maybe you can prove this, because the way we selected the weight functions, this is an old lemma that is not too hard to prove. For any collection of n to the power 4 cycles, some weight function in our family will assign non-zero discrepancy to all of them.
N to the 4 has to be relevant to the fact that you take k up to n to the 4. You can put any number there, and this k has to be large.
Exactly. Very good. So maybe I can explain that. So suppose you have like some cycles. So I want the discrepancy of the first cycle to not be equal to 0. This is some linear sum in the weights of the edges of that cycle. I want the discrepancy of the second cycle to not be 0. And I want, maybe have, I don't know, L such things. Okay, but if I take the product of all these, that should be non-zero. That's non-zero by the trivial weight functions we had here. This one, the one before I took the mod. Now I have something that is of value roughly 2 to the power of polynomial that depends on L. Now if I select that many primes as the polynomial, I'm fine. So that's the proof of this lemma. So this means that if we were lucky, if our graph only had n to the power 4 cycles, we are done. But that's usually, unfortunately, not the case, so let's see what we do. So what is a natural family of cycles that are most n to the power 4 that we at least can remove? You have seen what would be a natural? 4 cycles. Okay, so you see, so we can cope with all the 4 cycles. So let's start with that, and let's see what happens. So our first weight function, you give me a graph, now we select W1. I know that it's guaranteed to exist, so that all the 4 cycles get non-zero discrepancy. So in this case, I have 2 4 cycles, C1 and C2. Maybe my weight function is like that. So the discrepancy here, 3 plus 0 minus 2, so it's 1. Here's 3 plus 0 minus 2, it's 1. Okay. Now I have 2 perfect matchings that minimize this weight function, that green and the red. I want to look at the active subgraph, which is the graph containing an edge if it takes part of a minimum weight matching. So it would be just the union of the edge set of the matchings that minimize the weight function W1. This is the active subgraph in that case. What can we say about the active subgraph? It has no force. At least from this picture, looks like if I assign non-zero discrepancy to the 4 cycles, the active subgraph that contains the edge sets of the min weight perfect matchings has no 4 cycles. So what can we say about the active subgraph that contains those edges that are in a mean weight perfect matching? And that's the only place where we use bipartiteness. Okay? We will see that here bipartiteness is crucial. So bipartite key property, once we assign a cycle non-zero discrepancy, that cycle will disappear from the active subgraph. Here we removed all the cycles of non-zero discrepancy. Okay, so this is the toughest proof of their approach, but I think it's still quite easy. It's not, so it's 2 slides. So let's take it a little bit easy here. There are many different proofs. I can imagine maybe in this crowd I don't present your favorite proof, but I will present my favorite proof. So we will see if we can argue later. Okay. All right. So I want to prove that I find a weight function that assigns non-zero discrepancy to a cycle. I want to prove that this cycle disappears from the active subgraph. And I will use that by using the structure of the perfect matching polytope. So what happens here? So this is the convex hull of all the incidence vertices of perfect matchings. So all the vertices here correspond to perfect matchings. Now I select the sum weight function. I minimize it or maximize. Here, I guess it looks like I maximize it. Then, all the perfect matchings that is min weight perfect matches to this objective function will form a face of this polytope. So it will be the convex hull of these matchings on the corner. Yes, look at, you minimize a linear function, you walk. If it was normally it would be a single vertex unless you're unlucky, but here we are unlucky, so it's a face containing 3 perfect matchings. Now we want to analyze the matchings in this face. So the active subgraph is just the union of the edge set of these 3 perfect matchings. And here we will use that the perfect matching polytope is very clean. So it only contains, the trivial constraints, saying that, hey, in a perfect matching, you should pick one edge incident to each edge, each vertex, and each edge should be non-negative. So notice that this is all equality constraints, and the only inequalities we have is for edges, that they should be non-negative. So now it's known that the face is also described by setting a subset of the inequalities to equalities. So this means that the face here is just obtained by setting some edges to be 0, meaning that they disappear. That's the same as removing those edges from the graph. All right, so f is simply a subgraph. Some edges disappear, so f is described by setting some edges to be 0. All right. What can we say about the weight of two different points in f? So x is a convex combination of the perfect matchings that minimize w, and y is a perfect matching. It's easy, right? They have to be the same. They both convex combinations of mean weight perfect matchings. All the corners here have the same weight. So the convex combination of them have to be the same weight. So now I will prove to you that if there is a cycle that had non-zero discrepancy that is still part of the active subgraph, then I will construct 2 points in the face of different weight, reaching a contradiction. Okay? So that what we're going to use is that every x, y has the same weight in this phase, and that this describes the perfect matching polytope. Okay, so suppose towards contradiction that active subgraph has some cycle c of non-zero discrepancy, meaning that the weight of the green edges is not equal to the weight of the red edges. Define x to be just the average of all the extreme points of this phase, all the matchings of this phase. The reason I do this is because if I take the average of all the perfect matchings in the phase, I'm guaranteed that each edge in the active subgraph has a positive x value. Okay, so this implies that x is strictly positive for every edge. Now there is this quite standard argument to prove that bipartite matching polytope is integral. What do? We increase every edge a little bit and decrease every edge plus epsilon.
Every green edge you increase.
Yes. So we increase this with plus epsilon, minus epsilon, plus epsilon, minus epsilon. Notice that this satisfies all the degree constraints. We stay feasible. And it will, if I select epsilon to be small enough, it will also satisfy these constraints because all these edges was strictly positive. Okay, increasing red edges, or the other way around, one of the two. But you know, since the weight of the green edges will not equal to the weight of red edges, I will get a new point in my phase of different weight, which is a contradiction. Okay. So that's the proof. Okay. So it is here we are crucially relying on the bipartite perfect matching polytope is only described by these inequalities, because this preserves feasibility, because this is the inequalities we have to worry about. If we had more inequalities, we would have been in trouble. Okay, so if you lost me in the last 2 slides, what you have to remember is that because bipartite key property, once we assign a cycle non-zero discrepancy, it disappears from the active subgraph. And we have this old lemma that for any collection of n to the power 4 cycles, we can assign one of the weight functions from this nice family has non-zero discrepancy. Okay, so we already know how we selected W1. We removed all the 4 cycles. Now we know that the G1 has no cycles of length 4, the active subgraph of these matchings. The second step, I want to remove all the 8 cycles now. How many 8 cycles in a graph do you think there is of a graph that has no 4 cycles? You can do pattern matching because I select my weight functions from the same families. I think you can guess that there is at most n to the power 4 cycles of length 8. That I will give you the proof. You can think about it, but I will give the proof in the next slide. Okay? Okay, so now we have an active subgraph G2 without any 8 cycles. So now I will remove all the 16 cycles. Well, I remove all the 16, 12, 14. I mean, also the less than 16. But now we remove all the 16 cycles. And again, unsurprisingly, there's most n to the power 4 16 cycles in a graph without 8 cycles. Of course, in a general graph, there might be tons. But in a graph without 8 cycles, there is at most 16 cycles. And now you can see that you have this exponential nice increase in the girth of your graph, in the length of the shortest cycle. So after I select the log base 2 and weight functions, I'm guaranteed that the cycle has no cycles, and therefore it's only a single perfect matching. So remember, if I have two perfect matchings, they're alternating. No, their symmetric difference gives a cycle. So that's the whole proof. The missing ingredient is, why does a graph without 8 cycles have few 16 cycles? So let me prove that. I will prove this. You will see how clear how the argument generalizes. So we won't count the number of 8 cycles in our graph. We will just encode 8 cycles by writing down every third vertex in a cycle. Okay, so I start at A. I write down which vertex I have at A, the index. There is n possibilities, right? Then I walk one vertex. I skip that one, then I write down B. I skip that one, I write down C. I write down D. So there is a 4 tuple that I associate with each 8 cycle. Now I claim that, so for sure there's n to the power 4 different 4 tuples, because there's n choices for each element in my 4 tuple. Now the claim is that 2 different 8 cycles cannot have the same 4 tuple. All right. What would happen? Suppose I have another 4 cycle that has the same A and B. You know, if it's different than this cycle, it could be the same here, but it has to deviate at some point. And if it deviates here, it would go like that, creating a 4 cycle. But we just assume that there is no 4 cycles in our graph. So, you know, of course, it could be the same here, but then it deviates here, maybe, or one of the 4. Okay. So that's the proof. It's a very nice paper. Okay, so now we come to our proof, which is a little bit more messy. Okay, so some perspective, what happened? Yes, so we started off by having all possible matchings to be possible mean weight perfect matchings. So we had a convex hull of all perfect matchings. We selected the first weight function, minimize it. We ended up at some phase F1. Then on that phase, we selected a new weight function that we minimizes. And then on that phase, we selected a new weight function. And the key insight of measuring the number of weight functions we have to select is that the girth doubles in each phase. So I start with a graph of girth 4 maybe, and I end up with a girth that there is no cycles. And this follows because every phase is a subgraph. So the girth makes sense here. Okay, so let's see. So once you have this perspective, you can apply this methodology to any polytope. Okay, and we will see that there has been interesting work doing this on more general families of polytopes. And the polytope we're going to consider now is the perfect matching polytope of general graphs instead of bitype graphs. Okay. Well, the difficulty in a short sentence is that the bitype key property fails. So this doesn't work, so you have to do something else. But let me explain what's the issue. So the issue is that the perfect matching polytope for general graphs is, as before, non-negativity degree constraint. But now you have also, for every odd set of vertices, one edge has to go out. So, you know, if you have 3 edges, 3 vertices, for sure one has to be matched to some vertex outside. And these guys are in the description. So that's in Edmond's perfect matching polytope. You can imagine that maybe there was a smarter way of doing things, but in some sense, you know, Rothwell's result says that there's not a much smarter way of doing things. So you need to have many inequalities. All right, so before a phase was a subgraph, now it's defined by dropping edges and also setting some of the odd sets tight. Okay, because remember that a phase, when I optimize a weight function, is equivalent to setting some of the inequalities to equalities. Now I have these kinds of equalities, which means dropping edges, but they have also odd set inequalities. Okay, so yeah, we will see that girth doesn't make sense. So how bitype key property fails? Here's a graph. This is all the perfect matchings there are all. There are 4 perfect matchings in this graph. You either select one edge crossing or all 3 edges crossing. Now suppose I assign this weight function. This has non-zero discrepancy on all these cycles that uses 2 edges crossing. So in particular, this cycle C, it has non-zero discrepancy. So in the bipedal case, we knew that this cycle would disappear from the active subgraph. Let's check what happens in the general case. Notice that I have 0 weight here, and 1 weight here. So this matching has weight 1, right? This has weight 1, this has weight 1, this has weight 3. So it's only this guy that will disappear. Okay. But now the support of my active subgraph is the whole graph. Okay. So all edges take part of a perfect matching. So there is no decrease in the number of edges in the active subgraph. And this is an example by them, by the way, by Fenergy, Goya-Tiraf. So here, the new phase that you end up with F is characterized by one of these odd set constraints. Because notice that all these matchings select exactly one edge crossing that set. This set, for example, S. So the phase we are at now says you have to pick exactly one edge crossing this set S. So that, yeah. All right, so okay, so that's a problem. So we will see how quite technical proof that this is not really the bad guys. We can use them to our favor, okay? And we'll explain shortly. Okay, so the main ingredients how to overcome this is that I was like a little bit exaggerating. I said, oh, there's exponentially many constraints we have to worry about, but we know that these constraints can be characterized by a very nice subset. Every phase can be described by something called a lambda family, which means that they have to keep track of very few constraints. I don't have to worry about all the exponential constraints. And then
phase that arises in this
yeah.
that arises here.
Yes.
Not every phase. Edmond's polytope.
Yeah, in Edmond's polytope.
So what do you mean by every phase? Is every?
I think every phase you can uncross.
Every phase of what dimension?
Of the Edmond's perfect motion polytope.
Just the dimension of what? Every facet. Every phase.
Every phase.
But the whole polytope is also a phase.
Yeah, that's like the trivial lamina family, like empty.
Oh, the number of equality.
Yes. Yeah. Yes. Yeah, good point. Yes. The number of yes. Of course. Otherwise, otherwise I would be wrong, or Thomas would be wrong, and Edmonds would have made things too complicated. That's not the case. So, and then the second ingredient is that we will see that actually to have such a tight constraint is actually beneficial, and that was also used in the planar algorithm. Okay, so let me explain what the lambda family is. So we had here, every phase is given by setting some of the edges to be 0 equality and some of the tight odd constraints. Yes, so only the equality constraints I'm talking about. Now you can do something called uncrossing on these, so some can be chosen to be a laminar family. So here I've drawn the tight constraints. So laminar family means that you have each two sets are one is the subset of the other, or they are disjoint. So these two are disjoint, this one is a subset of that. You don't have like non-trivial crossings. For those of you that will
use laminarity, or you just use that it's small?
We will use laminarity. Yeah, because intuitively, yeah, I will come to it. Okay, so now we have a phase, we go to a subphase. What happens is that you drop some edges as before. So when you go to F1 to F2, you drop some edges, these edges disappear, and your laminar family increases in size. Okay, you add more odd set constraints. So that's another nice property. The laminar families that you get by going to a subphase are like consistent, that you can just add constraints to build up the laminar family. So, so that's what we're going to use with laminarity. And now let's see why these tight sets are actually good for us in some sense.
So at least this would show that it's after n steps, this would end.
Yeah.
You would add a constraint at least every time, and there are 2n minus 1.
Yeah.
More.
Yeah. Yes. And what is another way you can think of it is that once I add such a constraint, I can contract it because it behaves like a single. That's what they're going to come to now. It behaves like it decomposes the instance very nicely. So now suppose we have such a set S. What does that set S say? It says that any perfect matching on this phase we have restricted our attention to should have exactly one edge crossing here. So suppose I fix this edge. Now I know that none of these two edges should be used. So the instance decomposed into two independent instances. Okay, so now I have to find, in the remaining instance, I have to find a perfect matching between these two vertices and these two vertices. And that holds no matter which one I select. So I have basically 3 different options to decompose my instance here. Okay. Okay. So now our approach will basically be the following. Let's do the bipartite case. Remove all the cycles. We can do that plus minus 1 as long as there is no tight odd set constraint that interferes with this procedure.
Can you repeat again?
Yes. Maybe I have written it. Yeah. Yes. Okay. Between friends.
Just to understand the decomposition, if you fix the edge crossing to a particular instance in 2 instances at joint, if you fix it to another edge, you have different.
Yes. So there's n squared many ways of fixing this, but only polynomial. So now what I'm saying is that, you know, how did we do in the bipartite case? We we got the contradiction by taking plus epsilon, minus epsilon, plus epsilon, minus epsilon, plus epsilon, minus epsilon on some cycle non-zero discrepancy. This maintained feasibility because we only had degree constraints and not the odd set constraints. So this is still fine to do intuitively as long as you don't have a tight odd set involving here, right? You could have some set S here. Well, there it's okay. But that was a bad choice. Like you could have a set S here, then the outcut decreased by 2 epsilon. So this you have to worry about. But as long as I don't have tight odd sets, I can just replicate their proof intuitively. So between friends, that's what we're going to do. You have to worry a little bit that the graph is not bipartite, but that's like minor issues. Now suppose we removed all the cycles that do not cross tight odd sets. And let's do the simplest possible case. There is only one tight set. So this means that we have run the nice procedure by FGT to remove all the cycles that do not cross a tight set. So all the cycles in this graph crosses this tight set. Now I want to show that there exists a nice function from my family that isolates these perfect matchings.
So just before you run their algorithm, ignoring anything. You just use their weight function.
Yeah.
After the weight function, you know that there is no cycle that is. All cycles have 0 discrepancy unless they cross a tight set.
Exactly. You have to be a little bit careful just in the counting that you can get odd cycles. That's the only difference. Like, you know, when you said that the graph without 4 cycles have not many 8 cycles, because now you have odd cycles as well.
So what's the statement then? After you run their procedure, you just have no even cycles that cross.
Which is fine. You have to, what I want to say, you have to minor modify their procedure, but it's basically running their procedure, Run their procedures, we have no cycles inside the tight set. Now, how many perfect matchings can this graph have? I have no cycles here, and I have no cycles here. I claim that once I fix the edge crossing this tight cut, the matching is unique. Why? Suppose I selected this edge. There's 2 perfect matchings. That means that they have to differ on one side of the cut. Taking the symmetric difference will then yield a cycle on one side of the cuts, which we assume the graph doesn't have. What's that? Okay, so can I draw somewhere? All right, so I have my set S. I have no cycles inside the set S, and I have no cycles outside the SS. So now, suppose I fix the edge I want to be part of a matching. Let's say I fix E. Now let's look at all the perfect matchings containing this edge E in my phase. Suppose there's 2 different perfect matchings. That means both of them contain E, right? I have forced that, and they don't contain any other edge crossing the set S, because that should be at least exactly one edge crossing that set. So that means that, you know, there must be some alternating cycle either inside S or outside S. So, you know, the symmetric difference between these 2 matchings would be something like that. But this is a contradiction, right? Because I ran FGT, the previous procedure, to remove those cycles. So now I have at most 1 perfect matching for each edge crossing this cut. So I can have, in this picture, I can have at most 3 perfect matchings. But you know, if we are slopping calculating, we can have at most n square perfect matchings.
This is assuming only one type of.
Yes. So we start simple. All right. So now, is it clear? Maybe I don't know. You seem to follow well. So now, is it clear that there exists a weight function in our family that isolates one of these perfect matchings? So previously we said that one weight function is enough to assign non-zero discrepancy to n to the power 4 cycles. Now I claim that the same family will also isolate one of these perfect matchings. Why? Because I can take every pair of perfect matchings and write a non-equality. That's a linear constraint in the weights of the edges. And then I multiply it. So I will have n to the power 4 non-equalities again. Okay, so here, don't say entire matching. So at most n to the power 2 perfect matching, selecting one weight function now from that nice family will be isolating. Okay, so let me generalize this. So as Avi said, this only works when I have one. That seems extremely unlikely to happen. But that's not the general case. Let's generalize this one more step. So now I'm saying that instead of a laminar family, I have a chain, meaning that all the sets are subsets of one another. So here I have set S1, S2, S3, S4, S5, S6, S7.
I guess the previous one would work also if you had just they were disjoint. There were no containments.
That's more difficult.
You would have to pick one from every.
Yeah.
You may have one.
Basically, you would need to contract and rerun FGT or something like that. So now we have 8 sets here, or 7 sets, and it's divide and conquer. So how can we split these guys into 2 separate instances? Well, we would select an edge crossing the centermost set, because that would split it into 2 equal size instances. Again, there's n square way of choosing E, so we would get like n square. The tree would branch n square degree. All right, we continue to branch with f, n square choices of f, until we reach the base case, which is only one tight set. Okay. So now how many base cases do we have? Well, naively, it's n squared to the power of log, which would be fine if you work in Quasi-NC, but you can also be smart and see that all the base cases you will have will be consecutive layers. So you will have polynomially many base cases. So now instead of selecting, the n to the power 4, you need maybe n to the power 20, but you can still do the same weight to isolate them all at the same time. So now I've isolated the base, now I will walk up. So that's my first weight function. I select the weight function that isolates the bottom instances. And now I walk up. So now this part is isolated and this part is isolated. That means that after selecting F, the matching is now unique. There cannot be 2 matchings inside here, because that would again contradict that we isolated it in the bottom. So here again, we have now n square, a little bit more, like n to the power of 10 maybe, different cases. And that's how it works. So we select log n weight functions. So that's also why they get n to the power of log n processes. We get n to the power of log squared then, because we do this we have 2 log n's, one of the girth and then this divide and conquer approach. Okay. And that's basically the proof. Okay. Now, the only missing piece is like, how do you do if it's not a chain, right? So then what we do is to go from sets of size lambda to sets of size 2 lambda.
Sets, you mean odd sets?
Yes, odd sets in the laminar family. So now I have...
you can lift it and you can also erase.
Okay. It's very tough. Okay, so what I'm saying is, this is now, I'm very happy if you follow up to this point, but say we have isolated everything of size at most lambda in our laminar family. Now I want to isolate everything up to size 2 lambda, meaning once I fix I have a set S here of size at most 2 lambda. I want that once I fix the edge crossing this cut, it should be unique matching inside here. I already did it for all the sets of size at most lambda. But now, how many children, let's say strictly less than 2. Oh, that's fine. So how many children can this set S have of size strictly bigger than lambda? Right, these guys I already fixed, so they behave like vertices. So I can think of contracting them to vertices. But now how many, you can have at most one child of size at most lambda. So maybe that's the child. And this can have at most one child. So here you get the chain. So now we do the chain argument, and we do that log n times. Because every time you double the size of the sets of the lambda family.
So what are you isolating? So there's only one subset of size bigger than lambda, potential.
Yeah, there could be many at the same time, like disjoint.
In this set,
yes.
In this set,
yeah.
In the laminar family associated with the face you are thinking about, if there's a set of size 2 lambda, there may be several, but if there's a set, it can contain at most one bigger than lambda.
Yeah.
And then what?
So yes, so we are already fixed the guys of size at most lambda.
You isolated them.
We isolated, so that we can think of them as being contracted as vertices, because once you select the edge crossing that set, the matching is unique inside. So let's just think of them as vertices. Now, how can the lambda family look like here after contracting the set of size at most lambda? It must be a chain. And then we apply this divide and conquer. And that's the proof.
This is all in your head. You don't do anything about I mean, that's just the analysis.
Yes. Yeah. You show that you exist, but you, like they selected W1 to not contain any 4 cycles, we have selected some sequence of W's so that the structure is that. The analysis is tricky, the algorithm is trivial. You just run these guys in parallel. But you need many processors. That's the drawback. Okay, so, maybe I didn't explicitly say it in the talk, but I think I hope it was clear that this log n is a real barrier even in the bipartite case. Because we have this progress measure of doubling the girth. We have no clue how to, get rid of such an iterative. If you have some iterative argument, we don't know how to remove that dependency.
Is there any known lower bound for the oblivious strategy?
No, so you can do that in polynomial time, so at least there should be. The question is how to prove it. You can even do it in NC, RNC. Just randomly output enough weight functions. So this has been interesting progress. So by this viewpoint of the polytope, you can think of whatever other 0-1 polytopes family of 0-1 polytopes can we isolate. So it's been done for matrix intersection and more recently in totally unimodular polytopes by Guriev and Nishit. So totally unimodular generalizes, of course, bipartite matching, but there is not one that encapsulates all of them and the perfect matching at the moment. And here is an insane question that is very strange to me. It's a great question. Yes. So I would say it's an advanced exercise to adapt their algorithm to this problem. So this means that we have what's the problem? We are given a graph, even a bipartite graph you can think of. Some edges are colored red, and you're also given an integer k. And now you only have to decide whether there exists a perfect matching containing exactly k red edges. So you can do this in parallel time if you allow your randomization, but we don't even know a polytime. I don't know, so I try to think a little bit. The best I can come up with is n to both k, which is trivial. You guess all possibilities how you match the red edges, solve the perfect matching problem. I don't know if there's any smart. So the hope would be that can one use this iterative approach to get a quasi-polynomial? I don't know. Okay, thank you.